Okay, ready to dive in. Today we're tackling the world of PFAS, those forever chemicals everyone's talking about. And you've got some really interesting research on a whole new way to detect them. Not your average detection method, I've got to say.
Definitely a new approach, yeah. We're talking about a sensor fine-tuned enough to find one specific PFAS molecule, PFOA, amidst a whole sea of other chemicals.
That's like, what do they say, needle in a haystack? The needle's microscopic and the haystack's well, everywhere. But it's not just about finding the PFOA, is it? It's how they did it that's so cool.
It's pretty elegant, actually. They're using fluorescence.
Yeah.
Created a sensor that basically lights up when it finds PFOA.
Like a chemical beacon, sending out a big signal. And this beacon, it's built around this molecule, kind of a mouthful, actually, perylene denied, or PDI for short. I read that PDI is used for its colors, dyes and stuff. Never would have guessed it could be used for this.
It's funny how science works that way. Sometimes the most unexpected things, they hold this incredible potential.
Yeah.
But the PDI alone, not enough. They had to take it further, build it into something called a metal organic framework, a MOF.
MOF, right. So unpack that a bit. Metal organic framework. What are we picturing?
Imagine a sponge. Tiny, incredibly porous, and structured in a very specific way. In this case, built partly from our colorful friend, the PDI.
And held together with, what was it, zirconium?
Exactly, zirconium. And that choice of metal, it wasn't random. See, zirconium, it really likes to bind with carboxylic acid groups.
Which just so happens to be
a key feature of PFOA, like a locking key, zirconium. It's made to latch onto PFOA.
Okay, so we've got this tiny, colorful sponge, and it's primed to capture PFOA. But how do we actually know when it's found something? What happens?
So that's where the fluorescence comes in. It's a bit of a molecular dance, really. Normally, the PDI tucked away in the MOF, it's got this twisted structure.
Twisted.
Yeah, and this twisting, it actually dims the fluorescence.
Yeah.
But when PFOA comes along, gets into that porous MOF, interacts with the zirconium. It makes the PDI untwist.
So it's like PFOA unlocks the fluorescence. That's wild.
Exactly. And this untwisting, it causes this huge increase in fluorescence, a clear signal. PFOA is here.
This is blowing my mind already, and I have a feeling this is just the beginning. Did they test it out, this glowing sensor? How do we know it's reliable out there in the real world?
Oh, they tested it all right. Really put it through its paces.
Oh, yeah.
Exposed it to all sorts of things. Other PFAS chemicals, fatty acids, even like common surfactants, a real lineup.
Did it pass the test? Could it pick out the PFOA?
Aced it. Only lit up for PFOA. Talk about reliable.
Wow. So it's like having a sense of smell for this stuff just sniffs out the PFOA. But what about real-world use then? How sensitive is this thing? Like, could it find tiny, tiny amounts of PFOA, the kind that might be in our water?
That's the really impressive part. They found if they coated filter paper with it, with the sensor that is, they can make the signal stronger, sensitive enough to detect PFOA at, get this, 0.3.1 nanomolar.
Okay, for those of us who didn't take chemistry, how small are we talking, really?
Imagine trying to find a single grain of sand in an Olympic-sized swimming pool. That's how small.
That's insane. That feels like a total game changer for keeping our water safe.
Absolutely. With PFAS, the sooner you catch it, the better. And this sensor, it could make monitoring our water so much faster and cheaper. That's huge for public health.
That's amazing. But here's what I'm really curious about. This research, it kind of hints that these color-changing MOFs, they could have way more uses than just this, right?
You're picking up what they're putting down. This study, yeah, it was about PFOA. But the whole idea, using a MOF's fluorescence to signal, anything really, it opens up a ton of possibilities.
So you could have a whole bunch of these sensors, each one designed to find a different forever chemical.
Exactly. Like a custom detection kit. But it doesn't even stop there. What if, instead of just finding these chemicals, we could capture them too? Maybe even neutralize them.
Now, that would be incredible. Are people working on that already?
Oh, absolutely. This research, think of it like a starting pistol. The fact that we can design these MOFs to be so picky, it sparked so much new research. And everything from cleaning up the environment to, get this, delivering medicine.
So this tiny, colorful sponge, it's not just a detective, it's a potential superhero. Cleaning up our messes, maybe even revolutionizing medicine.
Right. Proves the point, doesn't it? Sometimes the biggest solutions come from the tiniest places. We always think big problems need big solutions. But this research, it shows that sometimes it's about understanding things at the smallest level, at the molecular level, that makes the real difference.
It's like they say, right, big things, small packages. Except here it's more like world-changing solutions in a tiny, colorful sponge. Amazing.
It really shows you the power of just following the science. They weren't trying to solve PFAS forever, right? They were just curious about these MOFs. And look where it led.
Yeah, a good reminder that sometimes the biggest breakthroughs, they come from the most unexpected places. But let's bring it back to our listeners for a sec. We've covered a lot, PFAS everywhere, this whole new way to detect them. What's the one thing you hope they take away from all this?
For me, it's that we're fighting back. These forever chemicals, they're a huge problem. But we're not just sitting here doing nothing. This research, it's proof that we can tackle this, one smart, creative solution at a time.
Couldn't have said it better myself. It's been fantastic diving into this with you.
Likewise.
And to everyone listening, we hope this deep dive has sparked your curiosity, that you're maybe even a little bit amazed by the world of chemistry and the discoveries still waiting to be made. Until next time, keep exploring, asking questions, and stay curious.